Yeah, thank you. Thanks for having me here. I apologize for the change in time of the talk. I got stuck in traffic. I thought 1 mile would not take longer than, I don't know, 30 minutes to get by car, but it took about an hour. So that was great. Anyways, so I will be talking about visual intelligence, mostly dealing with visual data, which is kind of, the biggest uh, at least volume-wise data out there. So I guess most of the talks talk about big data. This is like ginormous data. Just as an example, I think Roger earlier was talking about the Internet Archive, which has about 17 petabytes of data. Uh, Facebook in 2012 actually was receiving 7 petabytes of images every single month. So within 3 months, it was making up, much more than the Internet Archive, and who knows how much they're getting right now. It's always been growing. So I'll be talking about, how to deal with some of that data, as well as how to get something intelligent back from it. So looking forward. So, imagine you're on a vacation. You're with your son. You're taking a walk. Suddenly he turns to you and he's like, "Daddy, Daddy, I want McDonald's." And he's thinking of his Happy Meal. He really wants that. And you're like, "Sure, I can have a burger too. It's gonna make me pretty happy." So what's the first thing you do? You pull out your cell phone, and it's, oh crap, it's out of battery. This happens more often than not. And you're like, "It's fine. We gotta find McDonald's." You see his cute face, and you gotta walk your way there. So you walk, you end up at this intersection. Which way do you think might be the right one to go? Okay. I assume you guys know this. And then again, you're walking and you hit this intersection. So which way do you think you should go? You're with your son, you want to be safe. Probably the left one. So that's nice. You bumble around the city a little more, and finally you end up at McDonald's. Everything's happy, everything's great. So basically the idea I'm proposing here is that an image is much more than just a simple composition of its visual elements. So as an example, a lot of prior work in computer vision has focused on, given an image like this, let's try and label what's inside the image. So just something extremely obvious, like there's a Ferris wheel, there's a bunch of people there, what are some of the activities people are performing? But there's a lot more that we can get from an image. And the question that I ask in this talk is, how much farther can we go? So just as an example of different scales of how far we can go from just the obvious image, let's take a look at this image here. So some of the most obvious things people in computer vision have been doing for some time is, let's just label all the objects. Say, we have buildings here, cars here, and so on. Let's say we want to be slightly more precise. All right, we've labeled exactly which pixels belong to person, which pixels belong to car. But now let's try and get something a little more than just what is inside the image. Let's say we have this car here. We blow it up. So there's some part of the car that's occluded. So maybe we can infer, based on all the cars we have seen in the world, that's kind of what it would look like. And if I turn that car around, maybe it looks something like that. Hopefully more real, but you get the idea. So similarly, you can do this for other objects. And so this is, still right very close to the image. Now, let's say if I ask you to imagine what's the scene outside this particular image, people would have a pretty good guess, and I can imagine it would look something like that. So that's still staying really close to the image. Now let's take a step farther. Let's assume that image is taken from that part on the street somewhere, say in Paris. Now, what would the image of the street over there look like? So this is what you guys were guessing when you were trying to find McDonald's, right? You're not seeing a McDonald's in the image, but you're trying to infer where it might be based on the visual elements that are present in the scene. So that's exactly what this problem is. And now let's take a step even farther. So you have this image, it's anywhere on the interwebs, it might be taken in who knows where. Like Libya, you're seeing it in the US, and now we want to try and infer what is the impact this image has on you when you're looking at it. So, do you remember the image? Do you press like on the image? And so on. So that's kind of a big overview of what I'll be covering in the talk. Firstly, we'll formalize this problem of trying to find McDonald's. Secondly, we'll look at, can we predict how popular an image is going to be even before it's uploaded? The next thing is, can we predict whether people are going to remember a particular image or not? And lastly, can we, given all these non-visual elements, can we actually modify the image to affect these non-visual properties? So can I make an image, stick in your mind more than just what it normally would have? So let's begin by finding McDonald's. So given a map like this, so right now I'll formalize how we did the problem. So given a map like this, like Street View, we have a bunch of locations of McDonald's. So let's take a look at a particular location. We get, we sample images from random places on Street View. We see, look, those are the ones that are close to McDonald's. That's what they look like. And our task is very simple. We ask people, which of the two do you think is closer to McDonald's? So which one, any guesses here? I guess there's actually a McDonald's in the top image, so I hope everyone's going to say that. But essentially, we want to see whether this task is feasible at all to begin with, because it's such a weird, you wouldn't imagine that people would be able to do this, statistically significantly. And as well as we want to see if machines can do this, right? So we pit man versus machine. So we use our favorite crowdsourcing interface, Amazon Mechanical Turk, where you can just query a bunch of people about simple tasks or complex tasks and pay them accordingly. So we ask them, we show them two images and we just ask them, which one do you think is closer to McDonald's? So if they were acting at chance, we would get an accuracy of about 50%. And similarly, we can ask the machine, we give it an image, we convert it into some sort of representation that the computer understands. We apply our favorite machine learning algorithm and use that to predict what is the distance to McDonald's. So what happens when we try this? So fortunately, it did not, people were doing well above chance at about 60%. So about 60% of pairs of images, they were able to correctly tell that, oh, look, this one is probably closer to McDonald's than the other one, which was kind of nice. So we're like, could machines do the same thing? And fortunately, or surprisingly actually, machines performed even better than humans at doing this task. And then we tried it out in a bunch of other cities. So this was, again, using really big data. It was about, I think, 20 million images that we sampled from Google Street View, and we applied it to like a bunch of them here. So similarly, we see that in most of the cities, machines are actually able to outperform humans in understanding what's going on in this large data set to figure out which images are closer or farther from McDonald's. So this was just a simple task where you do a binary decision. But now, can we actually find our way to McDonald's? We really want that Happy Meal. So imagine I drop you at some random location in Manhattan, and I'm like, go, try and find McDonald's based on the visual cues you get from the environment. Don't talk to people or use your phone. So can you do this navigation task where you just step on these grids? That's how we set it up for the machine to find your way to McDonald's. And surprisingly, people are actually able to do pretty well. Compared to just doing like a random walk of the environment, people can get there many, many times faster. And there's another part of the result which shows that the random walk actually fails most of the time, while people are fairly good at navigating to within like 50 meters of a McDonald's, as well as computers which do a reasonable job. So we'll soon have a demo online at mcdonalds.csale.mit.edu, so you guys can try it out and see if you can find your way to McDonald's. So this was the first step, just looking right outside the image, or looking at the environment around the image. So the next one is, let's try and predict how many people are going to like a particular image. So what exactly is image popularity? So different networks have different notions of this. For example, on Instagram, it might be the number of people that like a particular image. On Facebook, it might similarly be the number of people that like it or the number of comments the image gets. So On something like Twitter, it might again be the number of retweets, favorites, and so on. But for this study, we used Flickr, which actually reports the number of views on a particular image, which to me is like a more pure metric, because there are many times you might open an image, but not necessarily click like on it. As an example, if your friend uploads an image like that, you might be, you might take a look at it, but you might not want to press like out of, feeling, for obvious reasons. Or for example, there's a funeral scene. It might be, you might open it, take a look, but pressing like may be not very nice, essentially. So whereas views actually gives you all of this. So as long as I've clicked on the image, it registers a view. So it actually tells you, like it gives you a more pure metric of what people actually look at. So why exactly does it matter? Why do we want to predict which images are going to be popular? So firstly, we want to do content distribution across our network. So if we can predict that this image is likely to get extremely high traffic, we can prepare for that. Secondly, I think this is one of the biggest problems, plaguing teens of this generation, is the problem of selfie selection. People take so many selfies, and they don't know which one to upload. Imagine if I could tell you, look, this selfie is probably going to get you more likes than this other one. Won't it just save them a bunch of time? Instead of spending hours, doing this, they could be studying or so. Another obvious application of this is also in advertising. We would, you want to select images that are likely to get popular. You want virality, you want to figure this out before you put your ad campaign online. So just as an example, this is one of an advert for funeral services. So there's actually a bunch of other applications of this, like video summarization. You want to understand user behavior, and so on. So how did we go about doing this? First, we generate a data set of 2.3 million Flickr images, where we just download a whole bunch of random Flickr images. We get the views on these images, and we use our same pipeline that we had before to try and predict how many views the image is going to get. So just using the content and ignoring a lot of the social features, which tend to have a big impact on these metrics, such as how many friends you have, like what groups you're part of, and so on. We just use the content of the image, which is something that people had not looked at before. So we want to try and figure out, using different types of image features, which ones are going to have a bigger impact. So for example, these are just some popular vision features, like texture, gradient, and so on. And deep learning features, which have recently become quite popular for those of you who may have heard of it. As well as some high-level features, such as the type of objects in the image. So surprisingly, we can actually do pretty well predicting, at a rank correlation of 0.4, which images are going to be more popular. But I think the more interesting part is looking at what causes the popularity. So for example, we can start looking at which colors tend to increase the popularity of images. So we tend to find more bright colors, more greens, more reds, and so tend to have a bigger impact as compared to the more greens and blues, which might suggest that indoor images tend to be slightly more, tend to have a higher popularity as compared to outdoorsy type images. So this is kind of the stuff people like looking at. The next thing is, let's try and predict let's try and figure out what objects tend to cause more or less popular images. So we use a similar pipeline as before, where we now, instead of having these complex image features, we have the object likelihood, which just says these are the objects present in the image. Now use this to predict what's going, which ones are going to be popular. And why we have to do this is because it's, my advisor was like, you can either finish your PhD, or we can use that money to label the 2.3 million images we have. So you know which one I chose. And instead, we applied the best computer vision algorithm we know to try and predict the objects instead of getting them labeled by hand. So these are some of the results from that. We find that some of the rare objects, such as having giant pandas or ladybugs, if you can find these, they tend to have a medium positive impact on popularity. But the objects that have the most positive impact are these ones. So, it's obvious why guys like them, and I guess girls like checking out other girls. So it's like universally acceptable, I guess, or universally popular. And then the objects that have negative impact tend to be like spatulas, so stop having spatulas in your images, or plungers, or the photos that everyone loves taking, possibly in this room, is with your laptop. Stop doing that. It does not help the popularity of your images. So this thing was actually pretty fun. So we decided to make a demo where people could upload their images online to check this thing. So within I think, it was on a bunch of media outlets and such. Within, I think, 3 days, we had about 300,000 images uploaded, which was awesome. And, we had a lot of content. But it was amazing to see how passionate people were about this. This is one of my favorite emails from the time. She had uploaded some images, and she was like, these girls, they deserve a better score. And she was extremely, into the calculator. And it was just nice to see, compared to most of the other research that goes on, how much people care about this stuff. So the next step is, first we were predicting popularity. Now so that was predicting what people like. But now we want to try and predict what people remember from images. So what exactly is memorability? So let me just define memorability as the likelihood of remembering a particular image. This is kind of boring, so why don't you guys, so I think the best way for you guys to learn about this is to participate in the experiment itself. So we will play a visual memory game. You guys are just going to clap your hands anytime you see an image that you have seen before. So images will flash 1 image per second, and if you've seen if you see the image in this sequence before, just clap your hands. All right? Everybody got it? Let me see those hands. Okay. You're not supposed to clap when it's okay. Okay, this usually works better. But yeah, all right, so you guys were clapping. So this experiment was conducted on Amazon Mechanical Turk, where people were seeing these repeats and pressing a key whenever they saw one. And memorability can now be defined as the probability of correctly detecting this repeat. So in this case, I put the repeats, maybe within 5 images after. But on MTurk, these repeats were about 100 images after. So there were many times that images were forgotten, but a large proportion of the times the images were remembered. So the really interesting aspect of this is if I now, suppose I have 100 people participate in my experiment, and I divide them into 2 groups of 50 people each, and plot the memorability, or this probability of correctly detecting a repeat for each of these 2 groups independently, I get a graph something like that. So you just sort it by the memorability. And the very interesting thing is they actually correspond to each other. So despite having completely random workers on MTurk who might be, I don't know, housewives in the US, rickshaw drivers in India, and people who are just participating from around the world, despite having completely varied backgrounds, the extent to which they remember different images is actually the same. So, you and I, the probability with which we'll remember a given image is actually a property of the image and not of the individual. So, which is really cool. And as we added more and more people into the experiment, that's the number of scores per image means each image was viewed by 80 or so people, the rank correlation between the 2 groups kept increasing. And there was a point where we kind of ran out of money. So, and you can split these 2 groups in any way you want, and you get a really high rank correlation every single time, which suggests that memorability is an intrinsic and measurable property of an image. And just another interesting aspect is look at the range of differences. So there's a lot of images that less than 40% of people remember, while there are some images that more than 90% remember. So there's just some images that tend to stick in our minds, while others are completely forgotten. And This means that we can actually start, playing with the content of the image to affect how much we will remember it, and starting to make a lot of low memorability images memorable. So, but before we can do that, we need to, be modifying memorability in a predictable way. So first, we need to be able to predict memorability. So first, we just tried some simple statistics, right? Like maybe having a really bright image makes it extremely memorable, or just having a lot of red in the image makes it memorable. But what we found is that there was not very much correlation with any of these simple statistics and what people remember. So the next thing we tried was, the standard computer vision features, and we were like, oh, this is pretty good. We're getting, somewhere. We can actually predict with a rank correlation of 0.5, while humans only have a consistency of 0.75. So we're, 2/3 of the way there. So that's pretty good. Now we're like, in computer vision and many other like fields like machine learning, what we have as ground truth is what people say. So we thought, why don't we ask people, what do they think they will remember? So we have this way, we have our study, we have some approach of measuring what they actually remembered. And then the other question we can ask is, what do you think you will remember? And we had to create a special place up top for how people performed. They actually behaved as good as random number generators. So people have no idea what kind of images they're going to remember. They just, like, we tried the question in many different ways, and this is the best kind of we could do. Most people are just guessing, which is actually kind of great, because that means that it has a lot of room for algorithms which can predict memorability to make a difference here. Because if I ask you to if I give you an image and be like, all right, use Photoshop or do whatever you want and try and make this image more memorable, you'd have no idea how to do it, because you don't even know what the notion of memorability is, and you don't even know how memorable this image is versus what happens after you make changes. While the algorithms can actually do a reasonable job at predicting this. So this is it's a machine learning task turned on its head, where humans are terrible at it. So that brings us to modifying memorability. So imagine if something like this was possible. Imagine if I could change the extent to which you remember images. How could this be useful? So firstly, obviously in advertising, right? Like imagine if I just had to show you an image once, you remember it, sticks in your mind. I've cluttered your mind with garbage, but you just can't forget this image. The other one is logos, right? People keep advertising and putting logos everywhere just in hopes that next time you see this logo, you have some brand familiarity. Now imagine if I can change your logo to just make it extremely memorable. So you show it once, people remember it. So these are some, I guess people would call it like adverse applications. But think about, good ones now. If in education, where we have a lot of content that we need to memorize, if we just changed visually how it's presented, we could make the task of remembering all this so much easier. Imagine if you had a harder time forgetting it than remembering it. Another obvious one, mobile applications. We just want to change all our images to be more memorable. Imagine a new memorable filter on Instagram. Or social networking, where we're posting all the things we do and we want our friends to remember it, as well as face memorability, right? Imagine a job application where out of some number of resumes, your face is the one that's remembered. So in this current work, I looked at modifying face memorability specifically. So given a face like this, can we actually move it along this memorability axis while still trying to preserve the identity of this guy? We don't want to lose him, but we want to change the image subtly to make it more or less memorable. So these are just some examples produced. So you can see, some of the lighting has changed. There's some minor effects that happen. Some slightly the eyes, the corners have changed, but it actually has a pretty big impact on how much we remember the different images. So over here, putting them side by side, you guys can see the differences. But if I, showed you one, then showed you the other, you'd be like, that's the same image I just saw. Which seems to suggest that the identity is preserved and so on. So how do we go about doing this? We have some space of a face, let's say x, where the face is parameterized by this x, and we can move it in this space. So just imagine, you have those points you can just hold and drag, right? Like you can drag it in different dimensions and such. So you can drag, like you drag it in one way, that's like, the guy's face becomes fatter. Another way, it becomes thinner, he looks younger, and so on. So you now have this space where you can start modifying a face. So we now define a cost function to, how do we want to change this face? So the first thing we want to do is we want to preserve identity. So if we change identity, the cost function goes up. Secondly, we want to preserve some attributes. So hopefully by the end of the modification, the dude doesn't start looking like a girl or or vice versa. And these two will keep the face exactly the same. So now we need a competing term which will cause it to have a predictable effect on memorability, which is again, which is the last term. So this term is going to say, the current memorability is x, we want it to be x plus 0.5, for example. And now try and modify the face under these constraints. So, I won't go more into like the math and such, but here are just some example results. So faces, I think these are just 3 results, but one of the things that you can see that's happening for more memorable faces is they tend to get like slightly thinner. The shape of the lips and such changes a little bit, as well as just the expression of the person has also changed. And a lot of these things are extremely hard to notice. Like if I gave you, I'll give you 10,000 images with memorability scores. Now go and figure out what exactly causes it. It's extremely hard to determine this by just staring at that data. Whereas for the machine, it's much easier to parse through all that data and identify what are some of these characteristics affecting memorability. And it's actually able to do it in a fairly predictable way. So out of all the modifications we made, 75% of them were completely predictable. So the graph, the blue one is showing the ones where we took a face and increased its memorability, and the red one is where we took the same face and decreased its memorability. And it's happening pretty consistently. So I guess the end goal is something like this, where we have an iPhone app where people are just able to twiddle their memorability around, as well as change. So there's some other attributes that we've been working on as well, like you want to try looking more confident, you want to look more intelligent, you want to look, all these soft attributes apart from the ones that are, I don't know if you've seen on the App Store, there's a lot of apps for looking just more attractive, and that's all, putting makeup and such. But imagine a whole bunch of other applications where you want to put this photo on your CV. You don't want to just necessarily look more attractive, but you want to be maybe more confident, more intelligent, and so on. And you can start hopefully doing this someday. So yeah, a lot of this work was covered again by popular media outlets and such, which was great. We got a lot of feedback and so on. So I guess just to reiterate what I had covered, first we started, our goal was to look beyond the visible scene, and we started by looking what is next to the image, finding McDonald's, and then predicting how people would react to a particular image, which is whether they're going to like it in terms of popularity or whether they will remember it. And lastly, how can we modify some of these non-visual properties by changing the visual elements of the image, which was the modifying memorability. So just want to thank my co-authors and funding sources and such, and obviously thanks to all you guys for being here.